In this video, we're going to try to determine the amount of sodium chloride that is dissolved in this 100 milliliters of solution. What we know is that the solution has a density of 1.07 grams per milliliter. We have 100 milliliters of the solution, and when we heated it up, that solution didn't boil until its temperature reached 102.57 degrees Celsius. Using just this info, can we find the grams of sodium chloride that were in that 100 milliliters? Go ahead and plan out how you might be able to do this. Forget about doing the calculations at first. Figure out a path, come on back, we'll talk through that, and then we'll give a chance to calculate it. All right, if you're back, well, we want grams of sodium chloride. That is our goal. How do we normally get grams of sodium chloride? Well, we could add or subtract grams from things, but we don't really have other weights. So often we tend to get it from the moles, molar mass. So more often than not, we need the moles of sodium chloride in a molar mass. Now, why might this be useful here? We know the boiling point. I have a solution, and it's boiling hotter. It does it because there's something dissolved in the water. So those moles of sodium chloride are related to the mole fraction of sodium chloride. Well, that could be found if I knew the mole fraction of water, which I could find based on the boiling point change. Remember that the actual vapor pressure is going to equal the pure vapor pressure times the mole fraction of that liquid. So if we knew the pure vapor pressure and the actual pressure, we could find mole fraction of water. Since the only thing in our solution is water and salt, well, one must equal the mole fraction of the water plus the mole fraction of the salt. So if I knew the mole fraction of water, I could find the mole fraction of salt, and well, there's a way we could use that to find the moles of sodium chloride. But I still don't know the actual pressure or the pure vapor pressure for water. Except we do know the actual vapor pressure. We're boiling, and we're at sea level. You boil when your external pressure matches the atmospheric pressure. So because we're boiling, the actual vapor pressure of water must be 760 torr, 1 atmosphere. What we really need is that pure vapor pressure of water. What would the vapor pressure be at 102.57? Well, we can solve that because we have a relation for vapor pressure calculations. Natural log of pressure 2 over pressure 1 equals negative delta H vaporization over R, 1 over T2 minus 1 over T1. Well, what do we know? If we say pressure 2 is our target, then we do know T2. That's just the temperature at which we boil. We want to know the vapor pressure at that temp. What would the pure vapor pressure of water be at 102.57? So if our goal is to find pressure 2, I know temp 2. I know delta H vaporization, that was in the problem. R is the universal gas law constant, 8.314 joules per mole Kelvin, which means what I need in order to calculate it is I'll need a P1 and a T1. I need some reference vapor pressure and temp. Well, we can always use the normal boiling point for the pure liquid. The idea is it would only boil at that normal boiling temp when it's pure if it matched the atmospheric pressure. So pure water, which is what we're looking for the pure water. Well, if I had pure water at 100 degrees Celsius, so 73.15 Kelvin, that would be 760 torr. We always have one reference. The boiling point for any compound is going to be when its vapor pressure is 760 torr when it's pure. When it's not pure, well, we need the pure vapor pressure to be higher so that the real vapor pressure is 760 torr. And so we could find it. We could find the pure vapor pressure at a hotter temp. We could plug in all these values, calculate out what P2 would be, use that as the pure vapor pressure. which means we could find the mole fraction and we could work backwards. This does involve a little step on how to go from mole fractions to grams. This is algebra. I'll give you a hint there. Go ahead and use this info, pause again, and see if you can calculate this out in full. All right, if you're back, well, to start with, let's do the part we can do. I've got Clausius-Capron equation. Let's plug in these values. Natural log of our target, so the pressure at 102 degrees Celsius, minus natural log of 760, which will be pressure 1. So remember your log rules. If you have two things divided, you can take the first log of the first thing minus log of the second thing. So we can separate them out here. That has to equal negative 40,700 joules per mole. So our delta H vaporization in joules because our R value is in joules. And our temps. Well, 102.57 in Kelvin is going to be 375.7 minus 373.15 Kelvin, the normal boiling point of water. Multiply this out. Natural log of the pure pressure at 102 minus 6.63332 is going to equal 0.089043. I'm going to add 6.63332 to both sides. We'll find that the natural log of the pressure at 102, the pure vapor pressure at 102 Celsius, is going to equal 6.72236. Take E to both sides. We'll find that the natural vapor pressure at our 102, technically 0.57 degrees Celsius, that pure vapor pressure at our new mixture's boiling point, that is going to be 830.77 torr. This might be slightly different depending on your calculator. Different calculators have different log tables and how they calculate, but as long as it's very close to this, we're good. Plus or minus a couple torr will be fine. Well, I have the pure vapor pressure. And we know that at our temp, the actual vapor pressure must be 760. So our actual vapor pressure at this temp must equal the pure vapor pressure times the mole fraction for our water. Well, it must be 760 if it's boiling, is the actual vapor pressure. If it had been pure water, it would have been 830.77 torr. So the mole fraction is reducing that. Not all of it is water, therefore not all of it will escape into the vapor phase, and so our vapor pressure is suppressed. What we'll find here is that the mole fraction of water is equal to 0.9148, which means we can find the mole fraction of sodium chloride. It's going to be 1 minus that. So our mole fraction of sodium chloride is going to be 0.08519. It's about 91.5% water, and it's about 8.5% sodium chloride. So we found our mole fractions. How does this let us then find the weight of sodium chloride? Well, we can think about something. When I've got a container and it's got some water molecules, it's also going to have some amount of sodium chloride molecules. In fact, this is the ratio of them. For every 1 full mole, so for every 1 mole total of particles, that's going to be the sum of the moles of water plus the moles of sodium chloride. Well, since I have the mole fraction, I know that out of every 1 mole, that's 0.9148 moles is water, and 0.08519 moles is sodium chloride. They must add up to the 1 mole total that we're assuming for this calculation. Now that's not what's actually in our container, but it gives us a ratio. And let's just say, hey, how much water versus how much sodium chloride, how much water versus total moles. But importantly here, it also lets us find the weight. Because if I know the moles of water and the moles of sodium chloride, I can find the weight of them. It's just them times their molecular mass. So times 18.016 for the water, times 58.44 for the sodium chloride. Which means we can find the total mass of 1 mole of particles of this mixture. We'll find that there's 16.48 grams coming from the water, and that there's 4.978 grams coming from the sodium chloride. If we add those together, we'll find that there is 21.46 grams for 1 mole of our mixture. This gives us a ratio. This will always be true. If I have twice the total weight of mix, I'd have twice the stuff. But twice as many moles with the same mole fraction will just give me twice the weight of the water, or twice the weight of the sodium chloride. These scale, which means we can set up a ratio. We can say that, hey, for every 4.978 grams of sodium chloride, there'll be 21.46 grams of the mix. I could have twice as much on top, twice as much on bottom, 4 times as much on top, 4 times as much on bottom, or some amount on top for 107 grams on bottom. Why 107 grams? Well, there was 100 milliliters of the solution, and in every 1 milliliter, there was 1.07 grams. We had the density, which means that weighed 107 grams total. I know that for about 21.5 grams, there should be about 5 grams of sodium chloride. So this is about 5 times as much stuff, so I should have about 5 times as much sodium chloride weight. Rearrange this, multiply the 107 up, calculate over, and what we'll find is that X grams of sodium chloride will come out 24.82 grams. So we had a mixture. We didn't know how much sodium chloride was in it, but we did know the boiling point, and we knew the total mass. I knew that, hey, I had 100 mils of it at this density, so I had 107 grams of it, and it boiled at 102.6 degrees Celsius. Using that boiling point info, we were able to calculate out the mole fractions, because the vapor pressure of the water is adjusted based on how much stuff is dissolved in it. And so we found what vapor pressure pure would have to be at that temp. We knew what our real pressure at that temp in the mixture had to be in order for it to boil. Using those two, we could find the mole fraction of water. If you know the mole fraction of water and there's only water and salt in solution, then you also know the mole fraction of the salt. If you know the mole fractions, you can determine some relative weights. You can say, well, say I had a mole stuff total, that would be this many moles of water, which would weigh this weight. That would be this many moles of sodium chloride, which would weigh this weight. Collectively, they would add up to the total weight of 1 mole of particles. If you poured enough of that container out to get 1 mole of just particles, that would be the weight. This lets us set up a ratio of 1 element to the total, which is really what mole fraction is. Remember that your mole fraction of anything is moles of that thing over mole total. Well, you can turn moles of a chemical into the mass of that chemical. And if you know the different parts and the different weights, you can even find the mass total. There's still a relative amount ratio. And so we could exploit that to find how many grams of sodium chloride must be in our weight of the mixture, based on the ratio of how much stuff was in 1 mole and its associated weight.